Hello everyone, welcome to the second episode of Dive into C++ 14. The first video was just a brief overview of some of my favorite new core language features. In this video, we're actually going to take a look at an interesting code snippet, which was originally posted on Twitter by Sean Parent, and this is the tweet. It's a very interesting piece of code, which looks quite scary at first, but let's dive into it and see what it does. So what does the function foreachargument do? Well, the name is pretty self-explanatory. Basically, you pass to the function another callable object f and a variadic pack of arguments, and the function is actually going to invoke f with every single argument that you passed. So for example, in our main, we're gonna call foreachargument, passing this callable object here, which is a lambda that takes in an x argument of any type. This is a C++ 14 polymorphic lambda, and prints it out to cout. And we're gonna also pass 4 arguments of different types. As you can see, this is a const char pointer, and these are 3 integers, and they're gonna be passed as variadic arguments to the foreachargument function. And if we compile the code, so just by calling the compile script, which compiles and runs, we can see that we get the hello 123 output. So what happened is that basically every single argument of the passed variadic arguments to the foreachargument function was forwarded to this lambda, and the lambda was executed for each passed argument. So this is very cool, but it's hard to understand how it works with this implementation. So let's move on to the second code segment, and here we can see the same code snippet rewritten in a more organized way, and I've changed some minor things as well. The name of the function is now forargs, as it is shorter and easier to read. Also, instead of using a variadic polymorphic lambda expansion, we're actually using an std initializer list here of int, and every element of the initializer list is actually an expression which is enclosed in round parentheses. So this is a single element of the initializer list. And as you can see, inside this element, we have our variadic pack of arguments, and it's gonna be expanded here. So we're gonna create n expansions of this element enclosed in round parentheses, where n is the number of arguments passed to margs, which is our argument pack here. So let me zoom out a little so we can see more of the function. And why are we using an std initializer list here? Well, we need a context where variadic parameter expansion can take place. And this can be any brace initializable container, such as an initializer list, but also C-style arrays such as bool or int arrays can work as well. And we're gonna need this context because we need to expand our variadic argument pack. Every single expansion will actually result in a call to the function mfn, which is the callable passed in by the user. And the function is going to be called with one of the arguments of the variadic pack. So we also need to evaluate this entire expression to an integer so that it can actually be stored inside the initializer list and not cause a compiler error. So we're going to use the comma operator here that will evaluate correctly this function call, but also result in an integer, because this is the expression that will actually be seen from the initializer list. Are you still confused? Well, let's try to make an example of an expansion of a forargs call. So let's say we're calling forargs with the same lambda as before, which basically prints the argument to std out, and we're calling it with 4 arguments. One is a C-style string, and we also have 3 integers. This call is roughly expanded by the compiler to something like this. As you can see, we have our initializer list. Every element of the initializer list is an expression enclosed in round parentheses, and every expression will have a comma operator. On the left side of the comma operator, we will have our function call, which is the lambda being called with every single argument that we pass to the variadic list here. And on the right side of the comma operator, we'll have any integer. In this case, it's 0, so that it can be accepted by the initializer list. And in turn, this code here is roughly the same as writing stdcout with every single argument. So the compiler converts this function into this kind of intermediate representation, which is the same as writing this. All of these conversions happen at compile time. So let's go to our main, and this is the same code as our example, and we can compile it to confirm that it's actually working. As you can see, this prints hello 123, and it is the same as writing this piece of code here. So if you're not familiar with std forward or universal references, I suggest you to take a look at this excellent article about both universal references and std forward, which you can find at this link. Let's move on to the next code segment. Well, I've removed all the comments from the forarchs function, so it is actually easier to read here. Let me just zoom in, and it doesn't look so scary anymore. We know what's going on. This is an element of the initializer list, and it gets expanded for every passed argument, and every expansion calls the function and returns an integer expression so that it can be accepted by the initializer list. So what is forarchs useful for? Let's see a potential use case. I don't know if you're familiar with the makeArray function, which basically creates an array where you do not have to specify the element type of the array because it gets deduced by the passed arguments. Well, we can create a similar function for vectors using forarchs as our building block. So makevector will be a function that will take one or more arguments, so it is a variadic argument pack, and it will return an std vector containing them. We will not have to specify explicitly what the type of the arguments is from the user code. So here we have our first problem. What type should we actually return from makevector? We actually need to deduce a type which is suitable for all the passed arguments. Fortunately, we have a type trait called common type, and C++14 introduced std common type t, which is an alias for common type that doesn't require the user to write the type name keyword and the colon type at the end. So for example, if we were using std add pointer, in C++11 we would have to say type name std add pointer of something, colon type, while C++14 introduced many versions of these commonly used type traits that end with the _t convention, and all we have to do is just say std add pointer _t of something, and we do not have to specify type name or type. As you can see, this is much easier to read, and it's also very useful when we are nesting multiple type traits. Std common type t actually finds out the common type among all the passed types, which is basically the type that all passed types can be implicitly converted to. So this is actually what we're going to use as our vector element type. Let's just use an alias here called vector item, and computing the correct return type is very easy. We just pass all the types of our variadic argument back here, which is called targs, to std common type t, and this will be the correct return type for our vector element. So we can just instantiate an std vector of vector item. We also know how many items we're going to put into the vector because we actually can get the size of the variadic argument back using the size of ellipsis operator here. So as a small optimization, we can begin by reserving the required memory into the vector. Now that we have our vector ready to store our passed arguments, we can use forarchs to generate the code at compile time that will emplace the items inside the vector. And this code is very simple. Basically, the function that is going to be called for each argument is this lambda here, which captures the vector by reference and requires an x argument, which is taken by universal reference, And this X argument is gonna get forwarded inside an emplaceBack call to the vector. And this function is gonna be called for every argument that we pass to our makevector function. So as you can see here, this is an example call to makevector. We're gonna actually instantiate a variable called v0 with automatically deduced type, and we're gonna instantiate it by using makevector, passing the 1, 2, 3, 4, 5 integer arguments. And this line is roughly equivalent to writing this piece of code here. We're actually instantiate the vector and reserving memory, which is this piece of code inside the function. And afterwards, we're calling emplaceBack on every passed argument. And this piece of code is generated by the forarchs expansion here. So we can also make sure that the type is deduced correctly by using std static assert and making sure that the decal type of v0, which is our vector returned by makevector, is equal to std vector int. And this will actually compile, so we're sure that we are actually deducing the right type. If we print out every single element of the vector, we will get 1, 2, 3, 4, 5. We can also do another example with strings. This is a set of 3 C-style strings, so the deduced type will not be std string but const sharp pointer. And again, we can print every single element and statically assert that the type is deduced correctly. If we want the type to be deduced as std string, we can only change one of the arguments to std string, and this will actually be deduced as std string because const sharp pointer can be implicitly converted to std string, but not vice versa. And again, we static assert here that the type is deduced correctly, and we print every single element. So let's run this code segment here. And as you can see, we get 1, 2, 3, 4, 5, which is this expansion. Then we get hello everyone, which is v1 expanded. And then we get hello world, which is v2 expanded. In the next code segment, we'll actually show another use case, which consists in iterating over std tuple elements. So our function will be called forTuple, and we can use foranargs as a building block for an std tuple element iteration function. But we actually require an helper function that expands the elements of the tuple into a function call. This is being proposed for the standard library as the function called apply, and there is a paper N3802 which is proposed by Peter Somerlad. Sorry if my pronunciation isn't correct. And you can find the paper at the following address. And they've just taken the implementation of the function from the paper, and here it is. We do not really know to understand how the implementation works, but basically when you call apply, you pass in a functor or a callable object and a tuple, and the arguments of the function call will actually be all the elements of the tuple expanded. But we actually need to call the function with every element of the tuple one by one, not all of them at the same time. So we can use forarchs in combination with apply to actually create a function that can iterate over tuple arguments. So this function is called forTuple, and it takes in a callable object here and a tuple. And basically what we do is expand the tuple into a function call to a variadic polymorphic lambda using apply, which in turn passes the expanded tuple elements to forarchs one by one, which in turn again calls mfn with every single tuple element individually. So this is what it looks like. We start by calling apply, and the function that we're going to pass through apply is this big lambda here. This is a polymorphic variadic lambda, which takes in a parameter pack of arguments, and this lambda actually calls forarchs, forwarding our desired function that will be called with every single tuple elements, and it also forwards all the elements of the tuple to the forarchs call itself. And the second argument that is going to be passed to apply is obviously the tuple. So here's an example call of forTuple. The first argument that we're passing to forTuple is a lambda that takes anything and prints out to std out. And the second argument is a tuple that's being built with std makeTuple containing various elements here. So this forTuple call gets expanded to something like this. It gets expanded to a foranargs call with the same lambda here, and the arguments of the tuple expanded one by one. And we are familiar with this syntax now, which basically gets expanded to 4 different std cout calls here. So again, the first argument is the function that's going to get passed to forearchs here inside the apply function, and the tuple is going to get passed to the apply function as its second argument, and the apply function is going to expand every single tuple argument and pass it individually to forearchs here, which will call the function mfn with every single argument. So we get something similar to compile time iteration of std tuple elements. So let's compile this code segment, and we actually get 10 hello 15c, which are the elements that we passed to makeTuple. So this is cool, but we are limited to unary functions. What if we actually want to take arguments 2 by 2 or 3 by 3? It is actually possible to create a more generic version of forearchs that takes the arity of the past callable function as a template parameter. So let's see an implementation of that in the next code segment. I actually lied. Before getting to the implementation of that function, we need to learn about a new C++14 library feature, which are compile time integer sequences. So what are integer sequences? Well, they are compile time sequences of numbers that can be expanded inside template specializations or function argument types. Positive integer sequences using std size t as their underlying index type are actually called index sequences, and they can be generated using std make index sequence. So basically, seek0 is a compile time sequence that goes from 0 inclusive to 10 non-inclusive. We actually need a way to retrieve the numbers stored into the sequence and expand them with the ellipsis operator. One way of doing that is actually using struct template specialization. So let's start by forward declaring a struct that will print an index sequence to the standard output. I will call it seekPrinter here. And as you can see, this is a forward declaration. This type name here will be specialized to an std index sequence of a variadic pack of std size t objects. So when we're going to pass the type seek0 to this struct, this specialization is gonna actually be mashed, and the index sequence will allow us to make use of the internally generated indexes by expanding this parameter pack here. So let's create a static function called print that will actually print our indices to the standard output, and we can actually use forarchs for that. And since we mashed the indices with this parameter pack here, we can just use the ellipsis operator to expand them inside the forarchs call, and every single index will actually get passed to this lambda that will print it to standard output. So let's try it out in our main function. We can try it out with seek0, which was from 0 to 9, and we can also just call make index sequence in place here with 5, which will go from 0 to 4. So we have these two seekPrinter calls. Let's try the code segment out. And as you can see, it works as intended. Index sequences are very useful because in many occasions where you would have used template recursion, you can now just achieve the same result iteratively by expanding a set of indices. So in the next code segment, we're actually getting to the implementation of our generic forarchs function that will actually pass the arguments to a callable object in groups of n arguments instead of one by one. And n will be actually specified by the user as a template parameter. The function is going to be called foranargs, And the implementation of this function was originally written by Daniel Frey as an answer to one of my questions on Stack Overflow. You can find the link here. And it is a very, very clever implementation that actually uses the compile time sequences to avoid compile time recursion, which can dramatically increase compilation time if it's used a lot in the code or if it requires a lot of expansions. We'll start by forward declaring an implementation struct of foranargs, which is called foranargs impl, and it will take as template parameters 2 different index sequences that will get specialized below. So this is our implementation struct, but we also need an interface function that will be actually called by the user and that will forward the correct index sequences to the implementation struct. And this is the foranargs function, which will take a size t template argument here, which will be the desired arity, which is basically the amount of arguments that we're going to pass in a single group to our callable object. And foranargs is very simple. In the implementation, we're actually get the size of the passed argument pack here using the size of ellipsis operator, and for readability, we're just gonna instantiate that into a context variable called number of args. We also need to make sure that the number of passed arguments must be divisible by n, where n is our t-arity parameter. We can do that by using static assert. Now we need to call the implementation function, which will be a static exec function inside our helper struct that we previously forward declared, and it's gonna take in as template parameters 2 index sequences here. The first sequence will go from 0 to the number of function calls that will be made, and we can actually calculate the number of function calls by dividing number of args by the desired arity. And this index sequence is generated like this. We simply pass the number of arguments divided by t-arity as our template parameter. The second index sequence will actually need to go from 0 to t-arity itself, which is actually the size of a group of arguments that we're going to use to call the function once. And this can be simply generated by passing t-arity to make index sequence. After instantiating the struct with the correct index sequences, we can call the exec static function that we'll implement in a minute by passing the callable object to the implementation, which is our desired function. And we also need to forward the passed variadic arguments as an std tuple. We are actually using forward as tuple instead of make tuple to avoid unnecessary copies and to maintain the correct reference types. And we actually need the tuple because we're going to use a combination of the 2 index sequences plus the std get function to correctly get the right arguments to pass to every single function call. So we can now move on to the specialization of the implementation struct and function that will actually match the 2 generated index sequences into 2 separate std size t packs. We can actually have 2 separate variadic packs in a single template if it is a specialization, as it will actually have no ambiguity. We will match the first index sequence here that goes from 0 to the number of function calls to this variadic pack here that's called tn calls. And we will match the second index sequence here that goes from 0 to the number of arguments to this second variadic pack here called tn arity. The exec static function will take in the function here that we're going to pass from the exec call inside the foranargs interface function, and it will also take the tuple by const reference, and the tuple will contain our variadic arguments. The first thing we need to do is retrieve the arity again using the size of operator of tn arity, and this will actually get the number of indices inside the sequence, which is our complete arity number. And for readability, we're just gonna store it into a context variable called arity. We also need a context suitable for expansion, as we did for the forarchs implementation here, and we're actually going to use a bool C-style array instead of an initializer list here. And for readability, we're just going to use an alias for the type bool array called swallow. And what we're going to do is expand the tn calls variadic index sequence to a number of exec and function calls. And we will actually pass as a template argument to xn the current index retrieved by the calls index sequence multiplied by the arity. And as our arguments, we're going to pass the function and the tuple. We'll also need the comma operator again to make sure that we do not get a compiler error, because we need the bool C-style array to contain bool expressions. So adding a comma true here will actually make all this thing evaluate to a boolean. And we'll use the ellipsis operator to expand this function. So it is not clear at the moment what's happening, but if you think about the multiplication operator here, we're actually passing the base index of every single function call that will be used to gather the arguments from the tuple using stdget. Again, an example expansion here of the above context will make it clearer and easier to understand. I'm just gonna remove this comment so that we'll actually see some color. We'll actually have an example expansion calling a binary function with 4 arguments. So we're gonna need to have 2 function calls, and every function call will have to forward 2 parameters at once to the function. Our function will be called fn, and it is actually a lambda taking x and y and returning the sum between these 2 numbers. And we are going to call foranargs here with the 2 arity. We're going to pass in the fn function, and as you can see, we need to pass the arguments in groups of 2. The first group will be 0 and 10, and the second group will be 20 and 30. This foranargs call will start by expanding this wall of context here, and this expansion will roughly look similar to this. So we start by taking all the arguments and putting them inside a tuple. This is obviously pseudocode, and we're going to have the tn calls variadic index sequence expanded, which is the number of calls that we require, which is in turn the number of arguments divided by the arity. So in this case it is 2, and we're gonna have an expansion with 0 multiplied by 2 here, and another expansion with 1 multiplied by 2 here. And the rest of the code is the same for every expansion, which is just passing the function, the tuple, and using the comma operator to evaluate to a boolean expression. As you can see, this is the base index of the function call that will actually use stdget to get the correct parameters to forward to our desired function. So in this case it is 0, in this case it is 2, and by using the arity variadic index sequence, we can go from 0 to 0 plus 1, 0 plus 2, and here we can go from 2 to 2 plus 1 and 2 plus 2, and correctly get these 2 arguments for the first function call and these 2 arguments for the second function call. So let's see the implementation of the execn function. So as you can see, we take the base index as a template parameter, and it still needs the function and the tuple. And the function call is very, very easy here. We just need to get the base number, which is the first index that we're going to use stdget on, plus the tnarity index sequence, which was passed to the implementation function here. And this is actually the variadic pack that we are expanding. It is a variadic pack of integers. So by using the ellipsis operator here, this is going to get expanded with the same base number every expansion and a different arity index here. So if the base is 0 and the arity goes from 0 to 2, this will be expanded to stdget 0 plus 0 and 0 plus 1. Here is an example expansion of this context here. Again, we have the same function that is being called with 4 arguments and a binary functor here called fn. This piece of code here that we've seen in the previous example expansion is getting expanded to this fn call, which is stdget of the base index, which is 0 here in both cases, plus 0 and plus 1. These 0 and 1 integers are gathered by the arity index sequence that goes from 0 to 2. And as you can see, stdget 0 will take this element here, and stdget 1 will take this element here, which are the correct elements of the first argument group. The second extend call will actually start with the 2 base index, and the 2 is going to get added to 0 and 1 to get the third and the fourth arguments for the tuple. And this is getting expanded to a fn of 20 and 30, which is the desired second argument back here. So let's go to our main function and take a look at some tests here. The first test is going to use a binary function, which will simply multiply the passed arguments and print them out. And we're going to call it with the following 4 groups of argument, which are 2, 1, 2, 2, 2, 3, and 2, 4. As you can see, we do not need std pair or std tuple. It will automatically group the arguments together based on the passed arity to foranargs template list. The second example will actually use a ternary function. We are going to pass 3 as our arity here, and it will just sum the 3 arguments and print them out. And we're going to call with 1, 1, 1, 2, 2, 2, 3, 3, 3, and 4, 4, 4. Let's try this code segment out. And as you can see, we get the expected results. This is 2, 4, 6, 8, and 3, 6, 9, 12. So this is interesting. I think it has a lot of possible use cases, and we'll actually see one of them in the next code segment. Like makevector, we're gonna implement a makeunorderedmap function. As an order map is an associative container, we will use a binary call to foranargs to actually pass key value pairs without having to specify a std pair or a std tuple, or actually having to explicitly specify the key type and the value type. This block of code is the implementation of foranargs without comments. And here we get to our makeunorderedmap signature. It will take a variadic pack of arguments, and as you can see, it will deal with deducing the correct key type and the correct value type. To do so, we actually need to call std common type for every even and for every odd passed argument. And as you can see here from this simple ASCII diagram, the keys will be all the even arguments and the values will be all the odd arguments. So we can use std index sequence to correctly get all these arguments here and all these arguments here and pass them to 2 common type t calls so that we can actually get the common key type and the common value type. To do that, we're gonna need an helper struct that is going to get forward declared with a single sequence type here and a variadic type name here that will take in all the passed arguments to the makeunorderedmap function. The index sequence will actually go from 0 to the sides of variadic arguments divided by 2, and we're going to use the index sequence plus 0 and the index sequence plus 1 to actually get all the even and all the odd arguments. So we'll need a specialization of common kv helper to actually get inside the sequence and retrieve the indices. And let's start by asserting that the number of arguments is actually divisible by 2 here. We need a way to get the type at a specific index from a variadic type list, because we know that the arguments are going to be at the following indices here, but we need a way to say, hey, give me the type at index 3, or hey, give me the type at index 4. Fortunately, there's a way to do that, and it's actually tuple element t, which is a standard function, or a standard alias rather, and to actually get the type from a variadic list which isn't a tuple, we can simply use a type alias that will wrap the variadic type list into a tuple and return the std tuple element t at the past index, which is called ti here, with the wrapped parameters into the tuple. So this type alias, inside our common kv helper will actually return the type at the specified index in the ts type list. To get the common type of keys, we can simply call std common type t with our index sequence multiplied by 2, expanded via the ellipsis operator. To get the common value type, we can do the same by calling typeat of the sequence multiplied by 2 and adding 1. Here's an example expansion for 6 types. So since we have 6 types, our index sequence will be 6 divided by 2, and that means it will go from 0 to 1 to 2. And the key type alias, so this piece of code here, will get expanded to something similar to this, which is a call to std common type t with typeat 0 multiplied by 2, 1 multiplied by 2, and 2 multiplied by 2, which is the same as typeat 0, typeat 2, and typeat 4. And as you can see, 0, 2, and 4 are indices of key types. The second expansion for the common value type will actually do the same thing as the key type, but add 1 to every single expansion. So we will get typeat 1, typeat 3, and typeat 5. And as you can see here, 1, 3, and 5 are value types. So we correctly deduced the common type for all the keys and the common type for all the values. We can also define some additional helper type aliases to generate the correct index sequences for the number of types, which is basically the size of the variadic pack divided by 2. And one last thing we might need is a convenient syntax to retrieve the common key type and the common value type that will actually create the helper for struct and directly return the key type, type name, and the value type, type name. So let's use some static assertions to make sure our implementation works. So if we call common key type with 2 arguments, the type will be simply the first argument, which is the key of this implicit pair, and the value type will be the second argument. If we call common key type with a variadic number of arguments, we can actually imagine having 3 pairs here. This column represents the keys, and this column represents the values. So what common key type will do is simply ignore this column here and retrieve the common type between the keys, which in this case is std string. What common value type will do is actually ignore the keys column and retrieve the common value for the values here, which in this case is float. Having this knowledge and this function, we can finally implement makevector, and it's very simple. We start by retrieving the common key type and the common value type, and we now know the type of the unorderedmap we're going to instantiate, which is an std unorderedmap of key type and value type. We can also reserve the correct amount of memory because we know that the number of pairs will be the same as the size of the variadic argument pack divided by 2. And we can now use foranargs with a binary function passing 2 as our arity to pass the elements 2 by 2 into a lambda function that will emplace them into the std unorderedmap as pairs. As you can see, this is our foranargs call, and our desired function will be a lambda that captures the result, which is the unorderedmap by reference, and takes in a key and a value argument by universal reference, and forwards these arguments inside the emplace method of the unorderedmap. Inside main, we can use the new C++14 std literals namespace, which enables the use of the s literal to create an std string from a const char pointer. And we can try out makeunorderedmap here by passing in the following keys, which are 0, 1, and 2, where 0 and 1 are std strings, and 2 is a const char pointer. and the following values, which are 0, 1, and 2.f. So this is a pair, this is another pair, and this is another pair. We can make sure that the type is deduced correctly by making sure that the decal type of M is actually the same as an ordered map of std string and float, which are the common key types and the common value type. And we can print out M with 0, M with 1, and M with 2 to make sure that the pairs connect correctly. So let's try out this code segment here. And as you can see, we get 0, 1, 2, which is the expected output. So thank you very much for watching this video. I hope you found the tutorial interesting. You can fork or look at the full source code on my GitHub page, and the repository is called tutorials. Check out my website for tutorials, projects, and to find out how to contact me. Thanks again for watching.